Right, welcome to talk number 3. And my aim in this talk is to, now that we've sort of covered some of the fundamental bits of physics and some of the theories, my attempt in this talk is to convince you that electromagnetism is the only thing that you've ever seen. In fact, I want to tell you that it's the only thing that anybody's ever seen or touched, and that it is the only thing which exists in the entire universe. So slightly contrary to the current standard model of physics, which says that there are 17 different particles, each one of which has its own field, I'm going to attempt to put forward my case that actually there is one field in the universe, which is electromagnetism, and that everything which exists is some kind of manifestation of that. So here we go. So to start with, what is electromagnetism? Well, essentially it's electricity plus magnetism. It's called electromagnetism because those two things nearly always come together. They are kind of inextricably linked. You might remember a little diagram like this from school, which represents a wire in green with an electric current going through it. And when you put a current through a wire, it creates a magnetic field around the wire. And this happens whenever any charged particle, in this case a bunch of electrons, but any charged particle moves, it creates a magnetic field. And the same is true in reverse. So if you take a charged particle, or you take a wire containing charged particles, and you move it into a magnetic field, or you move a magnetic field past it, it will create a force on those charged particles, creating a current. So it doesn't matter whether you put the current through the wire, that will create a magnetic field, but if you put a magnetic field onto the wire, that will create a current. So electricity and magnetism appear to be linked together in some quite fundamental way. So where do we see this in the world? Well, firstly, all electromagnetic waves of the electromagnetic spectrum are obviously electromagnetism. So that covers everything from radio waves, microwaves, infrared, the visible light that you actually see, all the way up to ultraviolet, X-rays, and gamma rays. So that is all electromagnetism. That hopefully is not contentious. A quick look at what that supposedly looks like. And obviously nobody's ever seen a photon because other than the light coming into your eyes, you can detect it, but actually to be able to look at it and see what it is and what it does, our best representation of it is something like this. So in red, there is an electric field, which is oscillating, in this case, up and down. And there will be there will be a magnetic field, which is always at 90 degrees to the electric field. So every photon, it doesn't matter which direction it's traveling or where it's going, there is always an electric field one way and a magnetic field at 90 degrees, and they are both at 90 degrees to the direction of travel. Now getting into physical things, whenever you touch something, such as sticking your hand on the table, the reason why you can touch it and the reason why your hand doesn't go through it is because of the repulsion between the electrons in your hand and the electrons in the table. So everything you've ever touched, everything you've ever picked up, you have felt because of the force of the electrons. Now that extremely rapidly with the distance, with the sort of it decreases with the square of the distance. So that repulsion is almost nothing as soon as you have any distance between you and the object, and it's incredibly large once you are effectively no distance from that object, which is why the table feels solid, even though that is just the electric force repelling you from the table. So this is the reason why you don't fall through your chair. It's the reason why your chair doesn't fall through the floor. It's all the electric force. So everything you've ever seen, everything you've ever touched, you have only done those things because of electromagnetism. Now coming on to some of the particles that we looked at last week, and we talked about quarks and neutrinos and those kind of things. I'm going to look specifically at the Large Hadron Collider and the things that it detects, namely the Higgs boson. But everything that it detects is in some way detected through some form of electromagnetism. So the Large Hadron Collider collides hadrons, i.e. protons, into each other. It uses magnets to send them round in tunnels very quickly and then smash them into each other. But you can't just look for a Higgs boson using your binoculars, although if you did, that would also be electromagnetism because it would be light that you would be seeing. But that's not how the Higgs boson is detected. The Higgs boson is detected with a massive detector. If you're struggling to get the scale of this, that's a person at the bottom of this photo in the middle, and that pipe running through the middle of this whole thing is this pipe here. So this is like a cathedral-sized detector. But everything that it detects, whether that's gamma rays flying out when particles decay, or whether it's electrons flying out or protons flying out, every form of detection is some form of electromagnetism, whether that's detecting the charge of the particle that comes out, whether it's detecting the energy of a gamma ray or some other photon that comes out, whether it's detecting the magnetism of a particle that comes out using magnets or electromagnets to detect that. We can only detect things through some form of electromagnetism, and then as the theory says, hang on, skip a step, we detect things through electromagnetism, and then we infer from the amount of energy that those things have that come out, whether we've detected that we think we've got an electron due to its electric charge, we can then work out its speed, and so we can work out its energy, or we've got like a photon coming out, we can work out the energy of the photon. And then using the theory that every particle is a quantum excitation of its field, we can say that from the energy of the particles which came out of a collision, we can infer what the energy of the particles were to start with, and then we can say, oh, we think the total energy of the bits that exploded were whatever they were. And so the Higgs boson is essentially detected by saying at some particular energy level, something weird happens. There's some anomaly at a specific energy level where the dog appears to jump in the air. So you end up with a graph, which is basically a graph of energy levels, and there's a lump in it in the middle where something different happens. And I used to know exactly what it was, and I've forgotten. But essentially, you get this bump in the graph. You're just detecting the energy of the things that came out of the particle collision. And if you look on this graph, you look at the scale along the bottom, that lump is at about 125 giga-electron volts. And if we look back to our table of all the particles from last week, the Higgs boson is a particle which pertains to an energy level of about 125 giga-electron volts. There's actually a divided by c squared there because it's measuring the mass rather than the energy. But essentially, we detect electromagnetism, and from that we infer that we think there was a particle there of some particular energy level. And the theory says that the Higgs boson only lasts for a fraction of a second. So as soon as it exists, it then explodes and decays into other things. And we detect the other things via electromagnetism. But the main reason I wanted to bring this table up again is because I want to point out the things which we actually know about all of these particles, which are these three things. So every particle in this table has a value for these three things. And that's essentially what defines each of these particles. They're defined by their mass, their electric charge, and their spin. The mass, as we discussed last week, and as I'll discuss a bit more in a moment, is the resistance to acceleration, essentially. I'll talk more about that in a moment. The charge is the electric charge, and then the spin is essentially a measure of its magnetism. For example, the electron essentially behaves like a tiny, tiny, tiny bar magnet, which is spinning. And it's said to have this sort of almost like a magnetic momentum, which is probably a whole subject in itself. But as essentially the spin relates to magnetism. So the three things that we know about all of these theorized particles of the universe is electric charge, magnetic spin, and their mass. So what about the mass? Because I think this is now possibly the remaining piece of contention in my proposal. So mass is resistance to acceleration. The bigger the mass, the bigger the force you need to create the same amount of acceleration. Mass is just the resistance to you trying to change the speed or direction of something. As I mentioned last time, the current theory of mass is that there is this Higgs field, and the Higgs boson is just a particular level of excitation of the field at which it pops out a little particle called the Higgs boson. But the theory is that this Higgs field is this kind of treacle field which attaches itself to all of the other particles and prevents them from being accelerated. So it gaffer tapes itself to every other particle. That animation went in the wrong order. My first problem with this is that the Higgs boson itself has mass. So if the mass comes from the Higgs field, that means that the Higgs field gives mass to the excitation of the Higgs field. It feels quite recursive. The Higgs field gives everything mass, but it also gives rise to the Higgs boson, which itself has mass, which must come from itself. That's not necessarily a problem, but I think it's worth noting. But I actually think that there's a different possible explanation for mass, which doesn't require the Higgs boson at all. It, unsurprisingly, just requires electromagnetism. So this guy, at the end of creating his theory of special relativity, he had a little afterthought, which was that energy and mass are equivalent to each other, hence the famous E equals mc squared. I think he realized this by observing that an object can lose mass by giving out photons, and that when one of those photons hits another object, that object gains mass from absorbing the photon. And so he concluded that energy and mass were interchangeable, and he came up with E equals mc squared. Just to pick that apart a little bit, make sure we properly understand it, to put it into words, energy is mass multiplied by the speed of light squared. We can rearrange that to give us a definition of mass. So mass is just energy divided by the squared, and the speed of light squared is a constant. It's just a number. It's a very, very big number. I assume he used C because it's a constant. So essentially, mass and energy are interchangeable, possibly, arguably, they're not just interchangeable, but they are actually the same thing. So I now want to give a few examples of where mass and energy interchange. And the first example is nuclear fusion, which happens in the sun and other stars, where hydrogen atoms combine to create helium atoms, and the resulting helium has less mass than the hydrogen that was used to make it, and that mass is what comes out of the sun as energy. So the sun is losing mass, which does mean that its gravitational pull on the Earth is reducing over time. But fortunately, that conversion factor between energy and mass is so incredibly vast that the sun is not going to lose any significant amount of mass relative to its size. We are not going to fly off into space anytime soon, but the sun is losing mass. The other next most obvious example is nuclear fission, where generally heavy uranium atoms decay into slightly less heavy uranium atoms, and that loss of mass is given out as energy. So the uranium that you take out of a reactor at the end of its life has less mass than the uranium that went in to start with. That is where the energy comes from. The same is true of chemical reactions as well, though. So this is a water molecule, two hydrogen molecules and one oxygen. And that water molecule has less mass than the three atoms that created it. And it is that loss of mass which gives out energy from chemical reactions. Most obvious one being combustion. So if you take usually carbon and hydrogen and you react them with oxygen, you will get out carbon dioxide and water and energy. And the energy comes from the fact that the constituent molecules coming out of the reaction have less mass than the ones that went in. And lastly, if you have something like a cup of tea or coffee, which is hot, it has less mass when it's cooled down than it did when it was hot. So all of those infrared photons coming out, which are effectively its heat, they are actually taking mass away from that cup of tea or coffee. So energy and mass are interchangeable, arguably actually the same thing. This is a raisin. I put it here just to demonstrate the conversion factor between mass and energy. So if you were to take all of the mass in a sort of standard size raisin and suddenly convert it all to energy, you would get more energy than your standard sized atomic bomb. So the conversion factor is vast, hence your cup of tea doesn't feel like it weighs less when you pick it up when it's cold. Just to sort of add another argument or another angle to my argument, particle decay only ever produces two things. One of them is other particles, and the other one is photons. So, for example, in going back to the Large Hadron Collider, when we have particle decay or the Higgs boson, if it exists, decaying into something else, the only thing stuff ever decays into is either other stuff or photons. So my proposal is this. I propose that mass is simply photons confined into 3D structures, and that therefore mass is energy. It's just energy which is standing still rather than energy which is moving at the speed of light. And there is one quite good argument against this, which is that photons don't have mass. If we go back to our table again, it is true, if you measure the mass of a photon, it doesn't have any. And I think this is probably the most common argument against this idea that everything is just electromagnetic. It's the idea that photons don't have mass. So where can that mass come from? Well, photons don't have mass, but they do have momentum. This is a picture of a solar sail, which is basically an incredibly thin sheet of, I think, usually gold. And it's spread out in space. You attach it to your satellite or your sailing boat or whatever you want to move through space. And this solar sail gets pushed along by the photons given out by the sun. So photons don't have mass, but they do have the ability to accelerate mass. They have momentum, strictly speaking. So yes, you can argue that they don't have mass, but they do have the ability to move stuff. And the standard definition of momentum is mass multiplied by velocity. And you can do some trickery with that equation, and you can swap mass. You can use E equals mc squared to swap mass for energy, and then you can sort of rearrange the equation to say, momentum doesn't require mass. But I think that that's kind of avoiding the point. It's just using sort of algebra trickery to redefine momentum as something that doesn't involve mass. Photons have the ability to accelerate mass despite not having any. So now this is how I think photons can create mass if they are confined. And this idea I stole from a YouTube channel called PBS Spacetime, which is great. And I will share the video that contains this idea afterwards, partly because they'll probably explain it better than me, and partly because it will give me legitimacy when somebody who actually has a PhD in physics explains the same idea. The idea is this: you have a massless box. That's impossible. You can't have a box that doesn't have mass. But supposing you could have a box and the box didn't have any mass, but it had reflective surfaces on the inside that were perfectly reflective. So if you put photons inside, the photons just bounce around forever inside this massless box of mirrors. The photons don't have any mass. The box doesn't have any mass. So you would think it doesn't have any mass. But if you imagine yourself taking this box and shifting it to one side, you would then find that if you were to shift it from left to right, that the photons hitting the left side of the box would hit it more numerously than the photons hitting the right-hand side of the box. And therefore, the box would resist you accelerating it. And resistance to acceleration is precisely the definition of mass. So you can take things which don't have mass, but if you create a confinement of energy, you create mass. I'll now argue against myself for a small moment, because as we covered in a previous talk, the speed of light should be constant regardless of whether you're moving or not. So if you shift the box to the left or the right, the photons should all actually hit both surfaces at the same speed. So I do think there's a slight flaw in this idea, but also the idea was proposed by someone who knows a lot more about physics than me, so I'm going to go with it. Yeah, my proposal is that mass comes from the confinement of energy to a space. Now I'm going to just give a couple more pieces of evidence to back up my case. First thing is that gravity appears to travel at the same speed as light. So this is a picture of two neutron stars colliding. I have no idea whether it's real or not, but it came from Wikipedia. When two neutron stars, which are incredibly heavy or massive, collide, they create such a change in gravity that we can detect that gravitational wave on Earth with some ridiculous, huge equipment. I don't quite understand but we do have gravity detectors. We can detect the gravitational waves of huge events happening in space. We can also see the light from this event reach us as well. And the gravitational wave and the light both reach Earth at the same time, despite having come over vast distances of space. And therefore, I think it's reasonable to conclude that gravity is in some way either an electromagnetic phenomenon itself or is governed by the same laws, probably by the same field. And my final argument is that you can literally make matter out of photons. This idea was proposed by two people, Mr. Bright and Mr. Wheeler. They proposed the idea that if you shove photons together and those photons have enough energy, you should be able to produce an electron and a positron pair out of those photons. Add in the fluffy particle zoo images we used last time, the electron and its evil twin, the positron, which is the same mass but opposite charge. And these guys proposed this idea, and it has now been done. People have literally created matter out of photons. The current theory of physics would say that the photons in their electromagnetic field then converted into the electron field. But I think it would be more sensible and simpler to say that the electrons and positrons are literally a manifestation of electromagnetism. As Einstein observed, photons can transmit mass from one body to another. So if they don't have it, how would they transmit it? This goes to the idea of waves. If you have ever played with the tin can telephone, you will observe that you can send a sound wave down a piece of string. That sound wave carries energy, but when the sound wave is gone, everything is back where it was to start with. There is no net movement of matter. There is movement of energy down the string, but afterwards the string's back where it was to start with. Nothing has moved, but you have transferred energy. And that is kind of the definition of a wave. A wave is something which transfers energy without a net transfer of matter. But if energy and mass are the same thing, and a photon is a wave, then a photon should be able to transmit mass without actually transmitting matter. So I will conclude by proposing a new view of the universe. What if photons are energy in motion, and mass is that energy confined to a space? Photons are waves, so they transmit energy without net movement of matter. They don't have mass, but because they can transmit energy, they can transmit mass. And the reason why objects can't travel faster than the speed of light is because essentially they are made of it. Gravity travels at the speed of light because it too is an electromagnetic phenomenon. And maybe, just maybe, there's only one field in the universe and not one for each of the 17 particles. That is my case. I now invite you to rip it to pieces.